Hello, welcome to my class on the basic of RF. In today's class, we'll be talking about RF mixers, and generally by literal translation of RF mixers. RF mixers are generally used in the lab to perform some signal frequency translation and nonlinear amplification. So generally in the lab, we use mixers for signal frequency translation and nonlinear amplifications. Well, how we mean by signal frequency translation, we will see it later. And what we mean by nonlinear amplification, we are going to see it there also later. So, but if you have been working with, you've been working in RF lab, you must have come across something. This is not a symbol. These are symbols, but you don't see symbols in the lab. So to better understanding in this class, I've made out some sketch. This is in 2D diagram of what we call mixer. So usually you have three ports of mixer, and one part of it is local oscillator. The second part of it is for intermediate frequency, and the third part is radio frequency, which is the output. And it could be the other way around. There are two types. When I take you back to the symbols, you will see that we could have different types of operations for mixers. It could be either up conversion or down conversion. This is one when we have in 2D. And when you have in 3D, you are going to see like this. So some of you who have been working in the RF lab, you must have come across something like this. Usually you connect this one to your signal generator. So here you have LO input, here you have the intermediate frequency input, and here you have the output, which is the RF output. So this is it, and this is what I've shown here. So whenever insider is denoted by 1, you should know that that is the portion of the LO. When it is denoted by 2, it could be this intermediate frequency, and when it is 3, it could be RF. So some manufacturer could decide to make it just give it a direct label of LO, IF, and RF, and other manufacturers might just decide to go by number, so 1, 2, 3, right? So this is what we call mixers. Whenever you go to the lab and you see some component like this, this is what we call mixers. Okay, good. So now back to our symbol level. So at symbol level, we have two things, or let me say two types of ways of using RF mixers. So in one particular form, it could be up conversion. And up conversion, that is when you are sending in an intermediate frequency as input signal. You're sending it into the mixer, and you are mixing it with a local oscillator. So those are the two inputs. One input from intermediate frequency and another signal as a local oscillator. You generate some frequency signal from local oscillator and you are sending it into the mixer. And you are receiving an RF output signal. This is a case where we call up conversion. This is a case we call up conversion. This is a case we call up conversion. And in another case, we could have, let me position the camera so you can see clearly. In another case, we could have a case where we have this as input, RF input signal, and we have local oscillators as also input signal, and you mix this one non-linearly, and you are outputting intermediate output signal. So this is a case where we refer to as a down conversion. So either of the way, generally what we are doing with mixers are just signal frequency translation and non-linear amplification. So we have to, for us to better understand these mixers, what we're actually doing, let's imagine we have let's imagine we have some given signal. Let's imagine we have a particular given signal. Let's say we have V. Let's imagine we have for derivation. Let's say we have V as an input signal. In this case, let's imagine we have V in like this, which is amplitude of in, which we don't know, just some signal, and then we say we call it cos in of t. We have this one, right? And then we have, let's say, for local oscillator as well, because we are generating local oscillator. Let's say we have VLO, which is ALO cos omega LO of t. So let me say this one is equation 1, and this is equation 2. Very good. So we have two equations, right? So let's imagine that we are mixing these two together, these two signals together. What are we going to have? So we're going to have something like this. We're going to have V in and VLO will equal to A in, right? Because we are going to have this one, cos omega in of t. This is one dot ALO cos. Let me position the camera so you can see what is going on clearly. Cos open bracket omega LO of t. Yeah, we have this one. So when we do mathematically, when we do this operation, what do we have? So generally we are going to have A in and ALO, and then in bracket we have cos omega in of t dot cos omega LO of t. Yeah, so we are going to have this one. So we are going to compare this one. Let's say, let's assume cos A cos B. So by mathematical operation, when we split this cos A cos B, when we split cos A cos B, we're going to be having equals to, in summary, so we have A in ALO all over 2. When we do the trigonometric splitting of this cos A cos B, then we're going to be having cos so let's open a big bracket, and then in plus LO, and then we have multiplied by t. Let's close this one, and then again let's say plus. So we have one part which is plus, one part which is plus, one part which is plus, and the second part would be A in, the same is amplifying again, A in LO over 2, and then cos. So again we have open bracket in of t minus, maybe rather we should write this t outside, better for us, minus omega LO, and then here we have t outside. Yeah, So here we have t outside. So we could rewrite this one so it could be clear properly. Let's rewrite it so we can get it clearly. So what we have is A in ALO all over 2 cos open bracket omega in plus omega LO of t plus A in ALO all over 2 cos open bracket omega in minus omega LO close bracket, and then we have t. So this is what we have. This is what we have. So when we talk about frequency translation, now you can see that we are having two frequencies mixed here as a sum, and here when you look at this one, we are having two frequencies being subtracted from each other. So two different frequency translation. Frequency when it's subtracted and frequencies when it is added together in addition form. And when we mean by nonlinear amplification, you can see now that these two amplitude, the amplitude of the in signal and the amplitude of the local oscillator signal, they are amplified, multiplied together, because you don't say you add them. So logically it's multiplied together and then it's half by the cosine formula, and also the same thing. So we have separate and two parts. So this is what is happening in mixers generally, and by physical picture, what you are going to see actually when you have something like this, what you are going to see is this chart. Let's draw a chart like this. So let's say here is the power rail, and there this is the frequency axis or frequency rail, whatever. And here we're going to have something like this. Here also, let's imagine we have something like this. So if I write here, maybe it's not so clear. Yeah, we can see now. So if I write here, I write let's say RF1, and here I say another RF frequency, RF2, and I put here as intermediate IF, intermediate frequency. We are going to have let's say here we have LO, because we use LO, local oscillator, or rather we could refer to as standing frequency, which is local oscillator, right? And then generally what we are going to have at as expression for this in picture form would be output, which is one frequency, which is let's say RF1, which we have here, will equal to FLO minus FIF. This is one. The second thing you are going to have is FRF2 will equal to FLO plus FIF. So, and those are the things we already have here. So this also could be, if I want to, I can rewrite this one in this form. So you can have FRF1 will equal to omega LO minus omega in, and FRF2 2 will equal to omega LO plus omega in. Yeah. So these are the basic. This is what is happening whenever you are sending signals into mixers. This is actually what is happening mathematically. This is what is happening. So you could either have, just in summary, you could either have your mixer in to be in up conversion, which is when you are sending intermediate input signal with the local oscillator signal, and you are generating RF output signal. Or you have a down conversion in which you have the local oscillator and the RF input signal to generate intermediate output signal. And this is the mathematical expression, assuming that we have input signal and the local oscillator combined together. We are going to have it mathematically like that. And the picture translation would be what you have explained here. So generally, in a common term, people refer to this as heterodyne, let's say heterodyne mixer or something, or circuit. So this is what we have. This is what is actually happening when you are working with mixers. So in our next class, we are going to talk about voltage control oscillator. But before then, I wish you the best in your learning. Bye.